So CAN protocol basically works like this. There is a CAN bus as a central bus, and there are few nodes attached to it. Those are devices. CAN is basically using mostly in automotive applications. It is present in your cars and probably even in aircraft pilots. I mean, aircraft pilot systems, etc. So what happens is lots of sensors and actuators, transceivers, many things are attached to it, and they all communicate through the common bus actually. So what that bus does is it'll have data in it, and whenever if somebody wants to transmit and communicate with others, it will just drop the message in the bus, and whoever wants to take it can take it, process it and put it back on the bus. So that's how CAN protocol works basically. And if you see in a car, you'll have something called as ECU, that is electronic control unit, or you'll have a TCU, transmission control unit. So, and there are sensors that are parking sensors, maybe airbag sensors. So many such things. All of them put data onto the bus, and whoever wants to take it will take it. And that's how the whole thing is communicating. This was actually built, I think, in 1983 or something, and this was mainly used to improve the safety systems of automotive, vehicles, basically. So what we are going to do today is we'll take a canvas, and then we want to track, who is, communicating through the bus. If I want to track a particular device that sends data onto the bus, how do I track it? We track it using something called as message ID. So the whatever message the device puts onto the bus, it has the data itself, and let's say a start bit. It has many things also, stop bits, maybe some other. It is appended with a lot of things, but just for simplicity and our FSM case, we just take a 3-bit message ID. We just take, and we'll add a start bit to it just to know that it is a message, completely a byte, not a byte, half word, so half byte. Let's take the example of, let's say, 110. I'll just share the screen, and let's say my message ID, as I said, message ID consists of the message 110, and I'm appending it with the start bit, let's say 1. You can append it with 0 also. You can take any message ID also, 10101. It's completely yours. So I'm just taking this. You can take a different one, but build similarly along with me. So now this is actually a state machine now. And please note, CAN protocol is actually very complex and way difficult than what we are doing here today, because message IDs of different units will be of arbitrary size, different sizes. So it is difficult to manage. And here what we are doing is taking a bus and just tracking one device specifically which is connected to the bus. So how do we do it? This is perfectly an example for a sequence detector. I want to detect the sequence 1110, and only then I'll get to know that, okay, that device is transmitting data or receiving data, or using the bus basically. And there is a lot of things actually, priority based. Those controller units which have more priority gets to use the bus more often than the ones which are or of low priority. So many things are there, but we'll not be going into that because that's extremely difficult to employ in Verilog. So basically what we're doing is an FSM, a mealy machine, where I'm going to detect this sequence to know that, okay, this device is using. So I'll take 4 states, that is A, B, C, and D. Just name them A, B, C, and D. Now let's say I'm in state 1, and it's controlled by let's say a clear bit. Whenever I clear it, it'll, whatever is the state of the machine, it will come back to the initial state, that is A. So what happens when I get a 1? So if my input is 1, so I'll obviously go to the next state, that is B. So my input is 1, but I haven't yet received the whole sequence. So my output is still 0. So that's how this works. And let's say I get another 1. So I'll go to the next state. So this is 1, and I have still got only 2 ones, this and this. I haven't got the whole sequence. So output is again 0. This is input slash output. That's the, not syntax, but that's how we write it. And the third one will be this way. Let's say I get another 1. What happens? That's a 1 again slash 0, because I haven't yet received the whole sequence. And finally, assume that I get 0 now. Now I get basically the whole message. If I get a 0, my output is 1. So I'll go back to the initial state and then look for the sequence again. Now what happens if I get a 1? 1, 1, 1, 1. My sequence is broken, right? So I'll go back to the initial state, but my output is 0. This is input and this is output. Similarly, we do the same thing for others also. If I'm in the initial state, if I've got a one, I'll go to the next state. If I get a zero, what will happen? I'm standing at the initial state, I get a zero, I'll be there only, no? So 0/0. I'll have to wait for the sequence again. I'll have to wait for a one until I start. Similarly, what happens if I'm on B and I get a zero, I get a one and a zero next. That's of no use, right? So we'll go back to the initial state and wait for the sequence to begin again. So that's 0/0. And I'm on C now. That is, I've received like two ones, but now I get a zero. That's again of no use. So what I do, I go back to the initial state, 0/0. And if I get a one, I'll go here. So that's basically it. You have just built your first finite state machine. And if you employ this in Verilog, that's when we'll be done. So are you all ready to do that? Yes.
Hello. Yeah, excuse me. I have
Yeah,
a
yeah,
doubt here.
yeah.
Yeah, with respect to the D transition, when the input is 1, why would it go to A? Like, wouldn't that make the sequence like it'd be 1, 1, 1, and then suppose we are getting another 1, it can just stay back at the same place, no? So that
Yeah,
if it gets a 0, then
yeah, I get your question. So
yeah.
there are two things called as overlapping and non-overlapping.
Okay.
If it is overlapping, I would probably stay in the same state and wait for a zero. But we are doing a non-overlapping sequence here. I forgot to say that in between. You can do that also. There's absolutely no
I
restrictions.
think no, I think what he isn't meaning overlapping.
Yeah, I'm
He's
telling.
meaning when we've detected 1, 1, 1, 1 4 times, so we should stay in state D only, no?
Yeah,
Because
you
Because
can
then
what
if we
if we
stay.
get
get
a
a zero?
yeah.
Yeah. That is basically what is overlapping, right? If I can wait for, okay, I'll tell you with an example. Hold on.
Overlapping is like 1, 1, 1, 0. Again, if you like, if the
Ah,
sequence overlaps, here there's no possibility of overlap only actually in the
yeah, see,
sequence.
what you're telling is you get a 1, 1, 1, 1. Okay. So you want to
Yeah.
stay in the same state, that is D, and continue, take these three as, the sequence, and then output is one, right? So that's what you're
Yeah.
trying to. That is basically
Yeah.
what is overlapping. I think, yeah,
Uh,
that is actually overlapping. So we are doing non-overlapping. So I'll anyway go back and start from beginning. I want perfectly 1, 1, 1, 0, not overlapped or not anything else. It's totally dependent on your choice. You don't have to follow this. You are free to do overlapping sequence. So this is basically overlapping sequence. If I have some sequence like this, I can try out. I can take this much. I can take this much. This is not a sequence. So that way, I think you're getting it right.
yeah. Okay.
Anything else? I mean, I don't think you're uh, convinced completely. Is it fine? Can
Like
I?
yeah, it's actually fine, but then like the way we had studied it was like, suppose the last bit is the same, then it's considered as overlapping. Suppose we have a sequence like 1, 0, 0, 1, and there if we have like the next bit coming as 0, then we can consider it as an overlap sequence because the first bit is itself is 1, so there the overlapping happens. But here it's like the last bit is 0, so after
Ah,
that I like I'm like not really convinced with
Yeah,
respect
according
to
to
this
how we know, there
called
is
as
no overlap
overlapping.
possible only in this sequence 1, 1, 1, 0.
Yeah.
okay.
Yeah, the four ones and zero, like the preceding bit of the sequence can be anything, zero or one. How is it
Mm-hmm.
considered overlap? Like if there are four ones and then a zero, our sequence starts from the second one. How can the
Yeah,
previous
sequence
one be
start.
counted as overlap? That's what is our
There was a
question.
previous sequence before also actually.
Yeah, if
This
there
is
was a
not
previous
tested.
sequence and the new sequence both have something in common, then that's overlap. Here it's
Do you
just
want
a
to read? I
preceding
mean,
bit.
do you want to iterate the cycle once and check if we are getting the correct answer? I mean, I probably think, I just built it today morning actually, so
Okay.
I felt it was correct. Uh, Let me know what exactly feels wrong here. Uh, I get a one, so I come to state B. I get another one, I come to state C. Then I get another one, so that's my third one. And
No,
if I get a
until we get a zero, we should stay in that loop. No, because we are
Okay,
getting one one.
I'll give this sequence where it is, well, first we get a 1, we go to B, we get a 1, we go to C, we get a 1, we go to D, then we again get a 1, we go to A, and now we get a 0.
oh, okay.
Yeah,
Uh,
so there the output should be 1 because we are detecting that sequence 1, 1, 1, 0, but then the output is coming as 0.
okay,
That's
yeah,
why
that.
from D
That's why
after
at
one, it
D,
should loop back to D.
yeah,
Okay, oh yeah. So you at D, if you get a one, you want to stay here.
Yeah, one with
yeah,
output
yeah.
zero.
with output 0. Okay, okay. And if you get a 0, then go over here and there's not. Oh yeah, yeah. Okay, that makes sense. This should seem fine, right?
Yeah.
Yeah, this is correct actually. Yeah, sorry for that. 4 1s and okay. Yeah, the same's correct. You okay with it? Anybody else? Any other you know queries regarding this? Let's go to our EDA playground and start building it. Okay, shall we begin? Okay, I'll name my module as so that will be module first. Module, I'll name it as probably canvas. That's it. Canvas is fine. And what are my inputs here? I'll as probably a clock. I'll have clear as well, and name. I need an input, right? So that will be, let's say, stream or something. And finally, an output. Now, output, if I want to use it inside always blocks, I'll have to put a reg to it, and then I'll name it as, let's say, output signal alert. Okay. So these are my ports. So these are the ones which will be interacting with external environment. And now I have to define parameters for the 4 states. I can use either parameter or now let's do something called as local parameters. Okay, these will be local to only this module. Even the test benches, I'm sorry, the other modules which are present in this design won't be able to use it. You can use parameters also. I'm just using it here so that uh, you get to know about this. But there's absolutely nothing wrong. I'm sure in your classes you would have learned with parameter and you name it as a, or first aid. People name it as got one, got one, got 111, and then got the sequence, something like that. You can name it anything you want. So that is one thing. I'll take a 2-bit values, that is 00. I'll just copy this line now. 2 bits are enough for 4 states actually, 00, 01, 10, and 11. That is one thing. I just paste it 4 times. 01, 0, and that is one thing. And yeah, I need registers for current state and the next state. And state. Note that they are 2-bit values, so it will be 1 down to 0. Yeah. So what we'll do now is, write an always block now, which will talk about only the state transitions. So I'll go for an always add, and what do I need inside? It will depend on my clock. So let's say positive edge of my clock, or maybe just clear. Clear is my signal. So what happens when either of these two should change? Obviously, I need to put a begin in. Inside this, if I go, initially I'll be at, okay, I've given it what name? Okay, state equal to A. Initially, use non-blocking here. And when should that happen actually? That will happen when my clear signal is high. Whenever I give a clear, my state should just jump to first state, that is A, and else what should happen to my
State should become next state.
yeah, exactly. Present state should get to next state. So state is my name, and that should go to. This is what happens just for the states actually. So we'll talk about what happens now. Now I need another always block, which will depend on my, since I'm writing a melee machine, it should depend on both input as well as my current state. So how do I do that? I take again an always block, always add, and what do I give here? I should give my state, which is my current state. If you want to name it, you can just name it curve underscore state, just so that you don't get confused. Totally up to you. Okay. Or what's my input here? Something called
Bit
as
stream.
data.
Bit
Okay,
stream.
bitstream. Bitstream. Okay, let's go. Stream. Begin in like always. So I have now. I'll use case statements to check each case. Whatever whenever is a state, at some state, what should happen next? If it is in B, then what should happen to when it goes to C? So that's how I do it. I'll begin with the case statement, and the case statement will depend on the state, that is current state. And yeah, let's begin. What's my first state? If the state is in A, then what is supposed to happen? Begin in here also, just so that
Excuse me.
yeah.
We've named all the parameters A. Shouldn't we name it separately?
Oh yeah, sorry. Thanks for that. Anything else which I'm missing? I hope not. Okay. We have begin. Oops. And end. So what should come in between? If I'm at A, what should what should be my output actually? My alert signal should be still 0. And what should happen to my next state? We are only talking about what is happening to my output as well as the next state. My next state, yes.
We need an if statement, right? If bitstream is 0, then
Yeah.
next thing
Instead of
is B.
you're correct. I'm using the conditional operator here. It's equivalent to
Yeah,
using
yeah.
if else statement. So I mean that just makes it into one line. That's it. If my bit stream, that's how it works actually. So I'll give things here. So if my bit stream is high, what should happen should come after question mark, and what should not happen should come after the colon. Yes, my next state should get the value of B,
B.
right? Yeah. And otherwise, if I don't get a 1, we'll check, if bitstream is high, then take B. If it is not high, take A.
A.
Uh, Everybody okay with that? That's how we use conditional operators. You might have done it in your C++ classes. Any questions here? I mean, anything at all, let me know.
One thing. So I joined late. Sorry for that.
Okay, not an issue.
Could you just go over what we are doing today? Like,
yeah.
go over the
First,
statement.
yeah, sure. So we just saw an application of FSM, that is CAN protocol. We'll be taking the CAN bus and then just tracking just one device. Whenever it sends a message, we just track it until just to know that okay, this message is from this particular device. So that's actually basically a bird view of application of CAN protocol. But we are using an FSM to simulate that. And for that, we are taking a small message that is 110. I'll append it with the start bit, or you can just say the whole thing is just 1110. You can take any sequence you want, and all we are doing is detecting this sequence using Verilog. That's what we've done until now.
Okay. Could you go over that one, the state machine thing? Yeah.
Oh, that one. Yeah. Oh, this one. Oh, one second. I'll just share my screen. Hold on. So we basically have 4 states. I name the states as 0, 0, 0, 1, 1, 0, and 1, 1. That's how I'm, naming them. That's A, B, C, D. So if I get a 1, I'll go to next state, another one, next state, another one, next state. And if I get a 0, I go to the initial state, but with an output 1. If I stay at the same, if I get a 1, I stay at the same state, so that my sequence can still become complete whenever I get to a 0 to get an output 1. So that's the all other are the other cases. If I get a 0, I'll stay here. If I get a 0, sequence gets broken, so I go back to initial state. From the C, that's the same case, and that is basically it. It's a simple state machine.
So that means when we have an output of 1, the particular device has sent the message.
Yeah, exactly. This is input/output. So whenever the inputs are, whenever I get the whole sequence 1110,
Mhm.
That's when I output a 1, so that I get to know that, okay, this is, I've received the whole message sequence.
Mhm.
That's what we're building now. And
Fine.
so we just finished our case A. Now if it's in B state, what should happen? Again, keep a begin end, and my output will still be 0 because we haven't received the whole sequence. What happens to my next state? Next state will again depend on bit stream. If bit stream is high, it should go to C. If not, what should happen? According to our state diagram, it should go to A. All right. That's it. We are done with B. I'll just copy paste the same thing. We will not waste time doing this. Copy. Anything? Yeah. Oops.
No, it's clear.
Always C. If I'm at C, my output is still 0. Depends on bit stream. If bit stream gets a if bit stream is high, then I'll go to the next state. That'll be D, and not. I'll go to A, and finally, what should happen actually? If I'm at B, there are two cases possible, right? Now things depend on input. Until now, output was 0, that is alert. Now actually, alert will depend on the state. Alert will be equal to what? Alert will be depending on the input. Sorry. Yeah, it's bit stream. Now, if bit stream gets the value of 1, what will happen according to our state diagram?
0, I guess.
Yup,
And
0,
then, or else otherwise 1.
otherwise 1. Everybody okay with this? What I just typed? Bitstream, we check the value of bitstream. If bitstream is high, okay, we just saw our state diagram also. If bitstream was high, then output is 0 and I stay at the same state. Otherwise, I go to state A and output is 1. And next state will be is that correct? Hopefully this is fine.
No, like we change that condition, right? Like the T part. So even that should be a conditional statement, like next state.
Oh yeah, next state also depends on that.
Yeah,
Oh
yeah.
yeah. Uh-huh. So next state will also depend on
Which tree?
bitstream. And bitstream, we just take the values. The next state will remain at present state. That will be, if bitstream is high, we stay at
D. D.
D, right? Yeah. D. Otherwise, it should be. If bitstream is high, output will be still 0 and we'll stay at the same state, that is D. Else, if bitstream is 0, that is sequence is completed, we get an output 1, that is alert equal to 1, and we go to the initial state back again.
Also, one more thing. A couple of things. So, what's that post edge clock or CLR? That one. What is that?
Oh yeah, that is called as sensitivity list.
Okay.
Pause at this positive edge of the clock. If
Fine.
you want something to happen at the transition from 0 to 1 of the clock, it is called as something called as edge sensitive. I'm keeping things head sensitive. I can also keep it, uh, level sensitive, like I'm doing for this clear. Clear is now level sensitive. Whenever clear is 1, only then do something. If it is positive edge of the clock, you can see in the waveforms also, we'll see that if the transition is from 0 to 1, do something. If transition is from 1 to 0, I'll give negate. So that's how we basically read it.
And why do we add the OR there?
Or is to check each and every condition. It's like logical, or I can or like it should
If
depend
this one
either on
changes
this
or
or on
this one
that or
changes.
on that way.
It's like if
It's a
if
syntax.
I
That's how we
changes
write
or
it.
yeah, okay.
Yeah, that's the syntax. Okay.
Fine.
Yeah. Now all I'm left with is to give default statement. So default statement, I'll keep my next state at A. That's the initial thing. That's it. I should give an end case probably somewhere. Where is my begin and ending? Begin, end. Okay, there should be an end case here. I'm missing out something. Yes, that's it. End module. I'll save this. I'll wait for some time. You can have a look at the code actually. I'll just. We are kind of running out of time. I'll give you the test bench in the chat actually. You can test it out by yourself. Uh, because we still need to do UART and that'll take a lot of time and that's a actually a Herculean task to build the UART transmitter. Are you all done with writing the synthesis code for the state machine? Okay, some of you have done it. So I'll just give you the test bench. Hold on.
So that parameter you're using just to yeah, like
Yeah,
compare the two.
I don't have to use the parameter. I can, I'll just show you. Hold on. Yeah, see, I can, like comment all this out. And then for every time I can, instead of A, I'll give 2-bit 00, 2-bit 01.
Okay.
Instead of doing that, I'll just rename it as ABC.
Okay.
I can keep this as something like, God one, just to, be specific, God 11. I can name it anyhow I want, like according to how we want it to be readable and, understandable. So that's the only sentence. Let's replace with something. So just look at the chat, guys. I'll just tell you, verbally only, orally, I'll just tell how the sales machine is working. So what I'm doing is, if anybody, forgot from yesterday's, all inputs are, clear and all outputs are wire type. And then you can see the word called as canvas. That's when I'm instantiating my module. And UUT is nothing but, you can name it anything, UUT, or you can name it Skanda or your own name. It doesn't matter. That UUT stands for unit under test. And I'm wiring up all the clock from my test bench to the clock to the synthesis module. And yeah, just replace that can data stream with the bit stream. Okay, that is while practicing I had used different name. Here I've given a different name. So just replace can data stream inside that. I just changed one. I forgot to change the other. Then in initial begin, that's where I give my dump file and dump vares. If anyone forgot, dump file is where the .vcd file goes, and .vcd is nothing but value change dump used for viewing the waveforms. And dump vares is to dump all the variables or selected variables. We'll just dump everything. In your EDA playground, what you have to do is take dump vares and just give a semicolon, because 0, TP is not required. That is only when you're using your local machines, your system or laptop or whatever. There, you have to give the path and all. But here on EDA playground, since it's on a website, it's not necessary. You can just give dump.vcd, anything. Just don't worry about that. And I'm also defining my clock. Initially, it will be 0. Then I'll take an always block. Always block executes until I give a dollar finish. So a dollar finish is a signal for the compiler to say that finish it, stop it. So that's where I'm doing. I've taken a time period of 10. That will be like 5 plus 5. So after 5, a delay of 5 units of time, I'm changing the clock to its negation. That is complement of it. Clock changes to not clock. And that keeps happening. So basically what I'm going to say is clock is clocking. And then an initial statement again with begin. What am I doing here? Yeah, I'm just clearing it after giving a delay. I'm clearing the, if some previous data is there, if some unknown values are there, high impedance, whatever, everything gets cleared from the state machine. And then what I do, I start giving the data stream. Replace all can data stream with bit stream, because we are using bit stream. Or if you want replace bit stream with can data stream, whatever is easier for you, doesn't matter. So you can see that I'm giving values actually 0, 1, 1, 1, 0. It will just give you the output, and let me know if that happens. And hopefully that should happen. I'll probably paste it. Any question? Anybody? Somebody unmuted, I guess. I'll do one thing. I'll change this to and data stream and data stream. I want to change 10-15 times. And data stream here also, and data stream here else. Oh god, I don't want to do this now. Just tell me if you're done. Sorry for that. That's like too much work. Just put a quick yes or no if the things are working. This is a tedious task. We still need to get into UART actually. More
There is
minutes.
one initial begin block which is just kept like that. Is that like, do we have to add a statement there, or it's just by
Sorry, I don't know how that came. Maybe I
Oh,
copied a
okay.
bit wrong.
Okay.
Okay, just forget that. I think that shouldn't matter.
I replaced candidate stream with bitstream in the chat.
What?
Could you show how it's run? Like yesterday, I could not like attend the whole thing.
Oh, okay, fine. I'll change things then.
I have put it in the chat. I think I didn't. Right.
Put the whole module synthesis.
Wait.
Okay, that's a test bench. Okay, no matter.
Actually,
I'll
the
change.
design we don't need to change, no, because we are calling with the dot operator, like dot bit stream.
Oh
That
yeah,
the
yeah,
name,
yeah.
yeah, it doesn't.
Yeah. Sorry. Yeah. Oh, that completely, out of my mind. Okay. Correct. I'll just change the.
Yeah, we'll just change it over there. Like instead of dot can data stream, we'll make it dot bit stream, and
I've
then.
changed it halfway, like literally everywhere.
I think you just have to change two places right now. Yeah, one there and then one at the dot bit stream.
And everywhere else, I think it's fine. But
Yeah. In
Okay.
the this one,
Just mention.
test bench. Yeah, in the test bench dot bit stream.
Also in the declaration.
That
Register.
is fine, I guess.
Yeah,
Oh,
that is fine.
That is fine. Anywhere else can. Blah, blah, blah. Okay. I think that should be okay. And have to select a simulator. Yeah. Anybody who didn't attend, select your simulator as Verilog 10, that one, and then open EP wave if you want to see the waveform. Since you have not given any, dollar monitor to, monitor the values, we will see the waveform. Save it. I don't know if any errors will come. Let's see. Oh. I don't have more than one simultaneous. There's some issue actually. Are you all getting something like, error can't do it because some timing problem? Matter though. Oh, crazy. So you're all getting it? I mean, can you all see this?
Yeah, what was the
Yeah, you
mistake
can
in
see the
yours?
state.
Like,
Huh?
what happened? Why wasn't it coming that time?
We have to give dump.vcd only. You
Oh,
can't. I
okay.
mean,
Yeah.
no. So yeah, you can see the next state and current state. It changes from 0, 1, 2, 3, 0, 1, 2, 3. That's basically happening, and I'll show you the output also. Hold on. Alert signal. See, it is 0, becomes 1 when you get an output. And then it will stay 0. Then again, there you can see the values. When it happens from the test benches. So 0, 1, 1, 1. So till here no output. Here you'll get an output that is 1, 1, 1, 0. Maybe after some 50, 60, I don't know, some 80 seconds. Hopefully, not sure. Somewhere around 80. Yeah, okay. At 60, you are getting it. No, 70. Yeah, 70. I guess 70 seconds have passed when I get an output here. Then I'll get here. Again, I'll get, because it is 1, 1, 1, 0. Then again, I'll get one here. And then it will be basically 0. So I think that is what I'm getting. Yeah. Last 2 cycles, it will be 0. And you can see the state transitions also here. State and the next state. 1, 1, 2, 2, 3, 3, 0, 0, 1, 1 again. So congratulations, you first build your FSM today. So I'll just start introducing the word. So UART stands for, anybody wants to tell? Have you all heard of UART?
Universal
You know,
Basic Rules. Yeah.
yeah, okay.
Universal
Others?
Asynchronous Receiver and Transmitter, I guess.
Exactly, universal asynchronous receiver transmitter. So what basically happens is we'll be doing it in Verilog. You can find it in Arduino or a lot. Arduino comes with SPI, even this, and I2C, that is inter-integrated circuits. SPI is serial peripheral interface. All of them are based serially output the data. So UART transmitter, how it works is, let's say there are two, I don't know, host machines which want to interact with each other. Or both of them have, transmission modem. Each of them have a transmitter and a receiver attached to it. Both of them. So transmitter of the first machine gets connected to the second machine's receiver, and vice versa. It's transmitter to the first one's receiver. So that's how it will be connected. I'll just show that also. There's an image. Okay. Now, how exactly is the data sent? There are UART is actually used for transmitting, ASCII characters, like English alphabets usually, but you can send other things also. I haven't tried, but this does work. Until recently, the data of ASCII character was sent in binary as a 7-bit, length, 7-bit binary code. It used to be, appended with the start bit and a stop bit, and in between, if required, parity bit that's used for error checking. So not necessary, but that's how it is. A data frame, that is, it can be anything. You can ASCII, or if you want, you can use a 8-bit word also. So that is 7 bits we'll be using. With the start bit, that becomes 8, and a stop bit becomes 9. So stop bit, just to verify that, okay, it is completely stopped. All the whole packet or the whole thing has been sent. Just to verify, the stop bit is usually, kept for 2 cycles, or you can say 2 stop bits. Both of them are, equivalent. So that's what we'll be doing here today. We'll build a transmitter. I mean, we don't have the time to build a receiver, but you can try it out if you want to later on. So we'll build a transmitter today, and that transmitter will output the data serially on, and then receiver will take it. That's its job. So all we have to do is serially output 9 bits of data. So how do we do that? First thing what happens is, initially whatever is the data to be sent, it's on a bus, and from the bus, the 8-bit data, okay, with the start bit, that gets latched into something called as a data register. We have a data register where all the 8 bits will be filled, and parallelly from the data register, it gets shifted onto the shift register. And now shift register's job is to append a stop bit behind, and then serially output one after the other. So all 9 bits will be sent, and then including the stop bit, and then if required, another packet, or if not, not required. So that's how actually UART works. We can actually start. I have a few signals which we need to know before, so that we need to know its importance, which we'll be using to actually build the transmitter. If there's nothing, I think we'll move forward. So what are the input signals? There is something called as a controller, which will output. It'll output a few signals and take a few inputs, and its job is to manage the transmitter. So what are the signals? Firstly, we have a signal called as byte ready. What does it do? It ensures that the bus has a valid data. That is, the byte is ready to be sent. Like all the bits of the byte, the data, the packet, basically, the data frame is actually correct, and it is available for sending. That signal, if you assert a byte ready, then that's what it means. Next, we have something called as LDTX data reg. What that means is load transmitter data reg. If this signal goes high, what happens? From the bus, you need to put it onto the data register. What I just explained, I'm just translating it into. So transmitter says, LDTX data reg. Load the transmitter data reg. So that's what it means. From the bus, you can put it into the data register. Now there is another signal called as T byte. T byte, what it does is it initiates the transmission of data byte. Okay, this is something which, except the host thing is there, right? It will tell the controller to do it. I assert the T byte signal, and then the transmitter can start the transmission of the data byte. And finally, I have something called as bit count. Ignore the capitals actually, like while doing the PPT, it got capitalized by itself. We'll be using small, or there's no difference. So there's another thing called as bit count. What it does is it will count the bit during the transmission. So that is one thing. Whenever bit count reaches 9, we have to bring it back to 0. So it will just count 0, 1, 2, 3, 4, 5, 6, 7, 9, and then back. So these are the 4 signals which we need to give as a host processor, and it will output some signals. What are the controller will output some signals for the transmitter to start sending. Now what are those? LETX shift reg, that is load transmitters shift register. I just told you that from data register, you need to put the content onto the shift register so that you can write shift all the data onto the serial output, and then that will keep going. So this signal ensures that that happens. There is another bit called a start bit. Okay. The start signals the transition. Once the the first bit is sent, that is start bit. Start also gets it gets asserted, that is it goes high, and then the transmission happens until it goes off. All the 9 bits are sent. Then there is something called a shift. This is a signal which tells the shift register TX shift reg to shift right by 1 bit. We are doing right shift here, and parallelly, behind what it will do, it will fill with ones. So once the whole byte is sent, the whole shift register gets filled with ones, and finally we have a signal that is clear. When that is asserted, the whole bit count which used to count till 9, that gets cleared, gets back to 0. Any question?
Could you repeat the working, like how it works?
Yeah, sure.
Would you explain?
First thing is transmission of UART1 is connected to receiver of UART2. Similarly, this will be act as a receiver. The first one will act as a transmitter. We are just building the transmitter controller. How things happen. How do you send the data?
Okay.
So inside, the there is the message, that is the data packet, which you can see on the right side.
Yeah.
All you have to do is
Nothing. I said yeah. Okay.
Okay, fine. Okay. So this packet is supposed to be sent to the receiver. Our job is to just send it without any errors and without any problems. So for that, we'll be appending a start bit and a stop bit also. And all our job is to do is send this serially outside our transmitter. That's all we need to do. Receiver's job is to receive it and decode it, and then use that data to do whatever it wants to do. That's not our business currently. So how do we do this? So initially in the UART, the processor has on its some data bus. It will have it. So in that data bus, let's say it has the 8-bit data. So what should you do? If you once verify using byte ready that this data is correct and can be transmitted, what you do is from this data bus, you put it into the data register first. Number one thing, you have to put it into the transmitter data register, which is TX. TX is short form for data register. From that,
so that basically acts as a buffer.
Yeah, a data register, exactly. That's acts as a buffer. It will hold it until you want it. It all depends on timing also. When do you want transmissions to start happening? That way.
Okay.
So from the data register, whenever you want to start shifting it outside, what you do is put it into a shift register, because that is what shifts it towards right side.
Yeah.
We are doing right shifting here towards LSB. The data, like let's say the data is 1011 101, something like that. So, rightmost bit, that is LSB, has to go first. Okay. Then it will just happen in the ultra direction. That's it. The LSB bit gets transmitted first, and later the other things. Okay. And another, this is basically working. You put it into shift register and start shifting until everything is done. Bit count will keep a count of it, and then it brings back to 0. And if you want to asynchronously do it, you have a clear signal that will anyway clear. If you want to stop at some place, or there's actually a reset signal which will like literally reset the whole transmitter. Like whatever is happening, stop. That's all.
Okay. And also like from the data bus, it gets loaded parallelly to the data register.
Yeah.
Using the the signal, the second one in the input signal, which you said. Yeah. Input should, yeah.
That is a load. It just loads the same data into the data bus. Data register. From the data register, it's a parallel transmission to shift register. From shift register, it's a serial transmission to outside, wherever it has to go.
Oh, okay.
Can we begin the Verilog programming now? Build,
Yeah.
come on. Yes. Let's get into EDA playground. I'll just share this tab instead. So let's start building it. Uh, let's take up this Herculean task of building. Okay. I'll just remove all of this. Let's see how much time we take to build. If we build it pretty quickly, then I think we can even write the test bench, or I'll just give you the test bench later. Yeah, let's begin. So first thing, module name. I'll call it probably say UART transcript. That's what we're building. Kindly, do it along me so that you can follow. At any point, if you want me to repeat, kindly let me know. I'm reiterating all of this again and again so that I want all of you to understand. That's the only motive here. Okay. So what and all do we need? Firstly, we need an input of 8-bit, right? 7 down to 0, so that will be 8 bits, and I'll call it data bus. This will be the bus. What else do I need? I need my input signals here. Be byte ready. What else was my input? I guess it was LED, X, data reg. That was another of my input. Other input was have a T byte or something. Yeah, that was T byte. Underscore byte. I would actually recommend you, like when I'm building it, just okay, I'll share the PPT also if you want later on. PPT actually is literally nothing except I just put heading slides. That's it. In case you want, just write down comments for this. Okay, the comment is you commented using 2 slashes. Okay, and then you can comment it what it basically does. If you want, I mean, if you're referring to the code later on, so that is one thing. You can do that. If I start typing, it will take a lot of
Excuse
time.
me.
Yeah.
Yeah, we can paste the code and then you can explain, no, so that it'll be faster, I feel.
If you want me to do that, I mean, if I was at your place, I wouldn't, paste the code and explain. If all of you, want me to do that, I'll do it. I'd actually encourage you all to like write the test bench yourself. I mean, it's okay. You can copy it for now, but after the workshop, I'll just sit at your house and then leisurely just write different test benches yourself. Just give different inputs at different times, change the delays, and then see what happens. Sometimes timing, if there's a problem, sometimes the output may not come. So just explore all of that. Yes, the test bench also. This is a pretty simple test bench actually. What I'm doing is a reset, and then giving the data on the data bus, telling data register go high, and then tell byte is ready, and then start transition, finish. That's all I'm doing. And clocking it. I mean, test bench is very simple here. There's absolutely nothing. Have you all typed the test bench? And I mean, I don't know. Some of you might have even like viewed the waveform and all. Yes. Okay, I'll begin then. Now, what exactly happens? We'll just go through the input output again. See, the data bus which had the 8-bit data, and then byte ready was the signal when the valid data is present on the bus, which is which can be transmitted. So that is the basically that signal what it does. And load tx data reg allows. I mean, when that goes high, that is when it is asserted. What happens is from the bus, the data gets into the tx data register, which I've defined here. This is not an input or output port because these are registers internally. This is excuse me. This is inside the module. This doesn't interact with external environment. And next we have t byte. This initiates this transmission. Okay, so this asserts and then transmission starts. So that's what it is. Now I have a question for you. Okay, it is universal asynchronous receiver and transmitter. Now why do I have a clock here? Anybody, any answers? And try to guess. Asynchronous basically means things doesn't depend on the clock. But why am I having a clock here? Any answers, please?
I guess it's because it doesn't have a clock for transmitting. Like externally, it doesn't have a clock for transmitting. So that is what it only has a clock for the controller.
Yep, exactly. Perfectly correct. And what that basically means is both receiver and transmitter will have their own clocks. Actually, there is an issue in receivers also. Receivers don't, since the thing is, both receiver and transmitter don't share a clock. That's why they're asynchronous. But internally, they have a clock, and that is used to actually use for shift registers. You don't want shift register to, shift like at random times. You want it to happen at perfect clock interval so that you can see the data shifting happening. So internally, it needs a clock to shift bits one by one, and after that, receiver is not connected to the transmitter through a clock. I mean, they don't happen on clock edges or clocks signals. Only thing is, internally both of them use a clock for their own shift registers, but they don't share a clock. That is why it is called as universal asynchronous. That is, receiver and transmitter don't share a clock. You're all okay with that? I hope that's clear. And let's get on to build this. I mean, yeah. So we have a clock for that. We have a reset. This will like literally reset everything when you assert this reset signal. And note that there is a underscore here. Underscore basically means that it is active low signal. You can, in case you get confused, you can actually name it as low underscore, or just to know that it is active low signal. Like when you pull it down, that is pull it to 0, then things get activated. That is the whole state machine gets cleared. That is, it gets resetted to the original state. So that is why this reset signal is used. Underscore basically, it is used for telling that it is an active low signal. That is, when you put it down, things get activated. If you pull it high, things are deactivated. So that is, inversion operation. It's just basically a NOT gate. That's it, with reset signal. And we have a serial out. Serial out is, it is a 1-bit value which will just take the LSB of the shift register and output it. That's why it is used. Okay, so these are ports which are important. Now, we have a few signals. We already discussed about these signals, what these do. Data register, TX data register holds the 8-bit data. Take note that TX shift register is a 9-bit value, okay? Because we append a stop bit at the end. So that is why this has it. And this register, this is for, sending the data registers contents to the shift registers content. I mean, put all that and with an appending it with the stop bit. So that is why it's used. And we have state and next state. This is for the state transition. And we are using a parameter. You can see that there is an idle state, there's a waiting state, and there's a sending state. We'll see. Okay, 1 second. So to view that, you can actually have your 2 bits also, but I'm just taking a 3-bit value just to like keep things simple. 001, 010, 100. So you can take anything you want. That's totally your choice, not a not a restriction at all. And we also have a bit count. Now to count, how many bits have been transmitted. For 9. To count 9 bits, we'll need a 3-bit value. So that's why I've taken bit count. And yeah, we have a clear and a shift and a start. Clear is to clear only the bit count. Okay. This clear signal, when you assert it, when you put it high, only bit count value gets 0. We'll see that we have written it actually. We have it somewhere.
Yeah, one doubt, regarding that state and next state, you have chosen it to be 3 bits, but it can be 2 bits. Like we can have it as 2 bits, right? Like, or is it necessary to have like a single one in the? Okay.
No, not necessary. Not necessary. And yeah, this is another important thing where I'm using a parameter called as all ones. So that is a 9-bit value with 9 ones here. You can also have it like 9. I'll just simply show you just so that you know. Use it on 9H and then like 1 FF. So that also works. Or 9-bit one. You can name it any way you want. That's what I'm trying to tell. So what this does is, once you have transmitted the data packet, like the whole thing, we backfill once, right? Okay, just we backfill with stop bits, and stop bit will get low when you're sending another packet. But if you're not sending another packet, the whole shift register gets filled with ones. Okay, so to fill all that with ones, I use a parameter to fill it. So that's why I use it. And now let's get to build this first line. Should I zoom? Anybody wants me to zoom this? Let me know. Is it visible? Because things go important now, like they're essential. Should I zoom? Just let me know, like zoom the page or anything. Yes or no in the chat. It's fine. Okay, cool. So I can keep this assign statement like literally anywhere I want in the whole module. I'm just keeping it in the beginning. You can keep it in the end also. What this does is keeps the serial outs value equated into shift registers LSB. So this is actually the output. Like that's what this does. Output is LSB of shift register. So that is what finally it should happen. Now all we have to do is take care of shift register. If you want to take care of shift register, we need to take care of data register. If you want to take care of data register, we need to take care of data bus, and that's how we backtrack. Okay. Now the most important thing is this transmitter depends on. I mean, there are three cyclic behaviors going on here. That's why we have three always blocks. Okay, always, and there is another always here, and there is another always here. We will see each of them. I've commented them also what they do. The first one is it synthesizes a combinational logic, and what that does is it will just assign values to next states and the outputs. Okay, it is a combinational value because all of them here are like level sensitive values. They aren't related to clock, so that is state. Okay, which state it is, and like bit count value, and whether t byte is asserted or not, or whether bit byte ready is asserted or not. So this is totally a combinational thing. This will synthesize. The next we'll go through this. The next always block. Yeah.
Sorry to disturb. Yeah. So, could you give a like overview of the module? Like that would help. Like I cannot visualize all the components which go into the module. Like
What
like
components?
For example, if I see a UART transceiver, I cannot like
A transceiver, like transit.
no, okay, sorry, the transmitter we
Okay,
are building.
transmitter. Okay.
Yeah. So like the inputs as well as the outputs, and like how are they related?
How are they related? Okay, I didn't get your question, but still, I'll try to answer. It
Okay.
basically is working off the UART again. All it has to do is, serially output the data. So for that, where does the data come from? That's why we have data bus, and if is the data correct? So for that, we have byte ready, whether it's ready to get transmitted. Then we have, to put it into data register, as a buffer, so that you can put it into shift register when you want. And then we have a T byte to initiate start transmission. I mean, that's all I can explain here. I don't get.
Yeah, that works.
That works, right? I mean, that's what you want.
Yeah.
This clock
Yeah.
is to shift the bits one by one in the shift register. So that only depends on clock, and there is a reset to reset the whole transmitter module, and there is a serial out which is a 1 bit value which gets the LSB of the shift register. So that's the basic process which is happening, and that acts as a to build this we need a state machine. Now what does a state machine do? It is either in an idle state. Idle is when it has all the data ready, but it doesn't get want to send. It is just sitting.
Yeah.
Now, what is waiting state? When it has the value in its shift register, it is just waiting to send, but hasn't yet sent. Idle is when it has it in its data register. Waiting is when it has in its shift register. Sending is the state machine stays in sending until all 9 bits are sent. And once that is in, the state machine fills everything with, backfills like one after the other and totally fills it with ones.
Okay. And then it goes
Is that
back
okay?
to the.
It goes back to the idle state. After sending, it goes back to the idle state. It has to go.
So the shift register which we are talking about is the TX shift register. The
TX shift register.
line.
Yeah,
Line.
I'll just write it somewhere for you. Yeah, okay, hold on. Transmitter. Okay,
Transmitter.
we just that's. If you see your Arduino module also, you can see like TX and RX will be there. I mean, instead of writing the whole transmitter thing, they just like name it like this. RX is that we don't have it in this yet, but I'm just naming it so that you don't get confused. I mean, it's not a something great technical term.
No, not that. I'm saying that the shift register which we'll be using in this code is in line 14. That's
in
the
line 4. Yeah, correct. Yeah, perfectly correct.
Okay. So like that way, like I wanted to connect things how the declarations connect to the actual placements, like how.
See. Okay, I know what you mean. Can you see these TX data reg gets the value of data bus?
Yeah.
Data bus, this is the value, 8-bit value. Can you see this? Data bus. If this is an 8-bit value, you can see 7 down to 0. And you also know that, I will go through this again, but I'm just telling you just for answering your question. Data bus, and you can see TX data register here. Okay. TX data register is right here. It's
line
also
13.
an 8-bit. Okay, so that value, whole 8-bit value gets shifted onto this. So that's the
Yeah.
only connection. I mean, that's how we do it in Verilog. It will synthesize in hardware by itself, using wires and all the other components. So yeah, we were in parameter. We just finished discussing about idle, waiting, and sending. And I'll just tell you, like in certain sense, like what happens again, but not in a bird's view. We'll go into little depth where I talk about these signals. Okay. So first, what happens is, let's say I assert the reset signal. Okay, reset will reset the whole thing. What happens if I reset the whole thing? The state machine goes into the idle state. It's better if you just write it down, or like uh, anything. What I'm saying here, like things are very important. It's better if you just know what I'm doing it. So when I assert the reset, it will go to idle state. You can see that in the test bench. Yeah, see, I'm resetting it once and waiting for some time and pulling it high so that it gets deactivated. So this is what I'm doing first. What this does is, once these two gets executed, what happens here? The state machine goes into the idle state, and bit count has to again goes to 0, obviously, because we have to start from beginning. And now what happens is the shift register gets completely loaded with ones. We are also doing that somewhere. All ones. Yeah, see, if reset is high, like when I do this, what should happen? Bit count should go to 0 because I'm starting from beginning, and shift register gets flushed with all ones. It means like there's nothing. So that's how we name it here. And since it's all the stop bits, when it pulls down to 0, then again transition starts. So that's how it goes. And next, what happens is, if clear is high, that is, if I clear only the bit count. I mean, things like clear. Yeah, see, clear is 0, and we also have to put shift to 0 because everything goes to 0. Like everything has to start from beginning. Start has to become 0, and load shift register is also 0. Okay. That is, don't shift any value into shift register. Why? Because it is filled with ones. You can't put anything there currently. Okay. Now what happens when I at some positive edge of the clock? Okay, we have that also. And if I assert the load tx data res, that is from load tx data res, what it does, it'll from the bus, it'll put all the values onto the data register. I just showed you, I think Satyam, I just showed that. Yeah, if this goes high, then what happens? Data reg gets the value of the data bus. Okay, this is like the buffer now. Okay, now what should happen next? If shift reg goes 1, what should happen? We'll discuss about this later. I'll just go the flow now. What we have to do in this idle state currently, we have the value in the data register. That's what matters. From the data bus, we have it in the data register. That's all what idle state means. It is idle. It has the values in its buffer. That is data register. If I assert the byte ready signal, what happens? If I assert the byte ready, if I'm in the idle state and I assert the byte ready, what it does, it ensures that the values are correct. And then what we can do, if I'm in the idle state, what am I supposed to do to go into the waiting state? If I'm in the waiting state, what should I do to go to the sending state? If I'm in the sending state, what should I do to send everything and go back to the idle state? So that's what the state machine is doing. If byte ready is 1, what and all are the things that should happen so that I go to the waiting state? So what I do, I put LDTX shift reg to 1. That is, you are allowed to put the data register value into the shift register value. And what should be the next state? Waiting state. Okay. Till here, I hope everything is clear. That means you are allowed to put it. Okay. The values can be in the shift register now. If I'm in the waiting state, that is, I have the values in my shift register, it is ready to get shifted, shift right through the serial out. So what is the thing which it depends on? T-byte. T-byte, initiates the transmission, is what I told you. Okay, initiates the transmission. If this is high, what should happen? Start is the signal which is used to signal that, okay, it is starting now. It is just a signal which will just tell, okay, kind of raising hand. Yeah, I'm sending now. That's what this start does. And then what will be the next state? It will go to sending. So you're allowed to go to the sending once T-byte is high. And finally, if I'm in sending state, if things are getting shifted, what should I check? I should check if the value is not equal to 9. Until then, keep shifting, shift, let the shift signal be high. Okay, that's what it means. Let it be high until it goes low. Else, what should happen? Clear. If clear is high, if I clear, uh, what is the else part? Else part is like if bit count is equal to 9, right? If bit count is not equal to 9, do something else. That means if bit count equal to 9, what should you do? Clear the bit count. That is clear. I told you clear all. Just flushes the bit count value to 0. All of that gets to 0, and then next state will be idle state. That means you're done with all the 9 bits. Go back to the idle state. This is what the state machine does. Default case, we keep it in idle. Okay, that is one thing. So this was the always block, which I told you, it is level sensitive and it synthesizes a combinational logic. You see, all of this is combinational. Nothing depends on clock, and there's no, feedback kind of thing. So this is combinational. Now, always at we're beginning with the now I'm supposed to synchronize the state transition of the controller. Synchronize what, with the clock and reset. So what happens here? If reset, if I pull it low, that means it gets activated because it is low, active low signal. What should happen? Whenever reset is pulled, state gets idle state. Okay, you should put it back to the idle state, whatever is happening in the controller. Else what should happen? If reset is not, if you don't pull the reset, what should happen? State should get the next state. Like anything happens to state, put it in the next state when all of the necessary conditions are met. So this always block takes care only of the state transition of the controller. If reset is pulled, then put it to idle state. If not, next state. Next state can also be idle state when time comes. That's how it is. Now comes, some of the most important parts. Now I have to synchronize the register transfers, from the data register to the shift register and shifting right, and such kind of operations is what I'm supposed to look after. Now I've taken care of the transitions, that is of the controller. I've taken care of all the state, when what should happen at what states. Now I have to take care of the transfers. We are kind of going into the in a certain order so that things go well. So again, if reset is pulled low, what should happen to the registers? Not what should happen to the state, or not what should happen to other things. We just care about registers now. Because register transfer is what we are thinking of now. If reset is pulled, what should happen? Shift register should be flushed with ones, is what we know. What should happen to the state? It should go to the idle state. In idle state, what will happen to shift register? It will be filled with ones. What is all ones? Take care that never we equate an 8-bit value to a 9-bit value. That is taken care of very carefully. Shift register is a 9-bit value, so is all ones. We named all ones as 9-bit 1111. Okay, so that is something which you have to take care of. And what should happen to bit count? Put it to 0 and end it. That's it. If reset is not pulled, what and all other things that should happen? So that's what we see here. First thing we check is the data, data register, the load data registers value is 1. Are we allowing the data registers value, from the data bus to the data register? Is it allowed? How do you check it? You check it using this signal, as I already told you. If this is 1, what should you do? Put the data bus value into the data register. Done. What else should I check for? I should check if shift register. If this signal is high, load transmitter shift register. If this is high, what should happen? What should get into shift register? I need to take data registers value. This is, be very careful. This is an 8-bit value, and I'm appending it with the 1-bit 1. Okay. Because 8-bit and I append it with the 1, together becomes a 9-bit, and then you can start shifting. Next, if I have a start, if start is 1, that is what was start?
One was, excuse me. Yeah. So that one was the stop bit, right?
Yeah. Oh yeah, stop it. Correct.
Okay.
Yeah. So we have a start, the start signal. If that is high, start, what does it do? It will just say, it's kind of like on hand raising signal. Yeah, I'm starting transmission. So that's what it is saying. If that is correct, then what should you do? Start bit. Start bit is 0. That's what we have it in this case. So start bit, put the start bit to 0. This is the first value. Okay, that goes to 0. And if you're clearing it, if clear signal is high, then put bit count equal to 0, because that's what it does. We have to define the functionality. I just explained somewhere before, but its functionality is given here. And finally, these are all the registers, right? Even bit count is a 3-bit, 3-bit register. So we have to take care of all such kind of registers. What are all the registers? Data register, that is tx underscore data reg. tx underscore shift reg and bit count. Bit count is a what type of register is it? It is a status register. It will just check the status of the transmission, that whole packet thing. If is the are all the 9 bits sent, so that is what it takes care of. That status is what it monitors. So bit count gets 0. Else if clear is 0 and shift is 1, okay, what should you do? If clear is 0 means what? Don't flush the bit count with zeros, and check if shift is 1. Is shifting still happening? Shift is high until and unless all the 9 bits are sent. Is shifting still happening? What should you do? Increment the bit count, because you need to, you haven't yet sent all the 9 bits. If only shift is 1 and we don't care about the clear, then what should you do? Append with the start bit. Stop bit. The shift register, its final value, like that will get appended with this and shift register. This is where basically, the shifting right happens, right shift and backfill with ones. That's what I said. You send the first bit, shift all the values towards right and backfill with one. Shift another bit with the clock signal, synchronize with clock, backfill with one. So that's how things happen. If I press a reset, in between things happening, it'll flush everything into ones. Like the whole shift register gets the values ones. Is the synthesis clear? Any questions?
Yeah, so the line 97. So that means
90. Hold on. Yeah.
The one which you have selected.
Yeah. Okay.
In that means the convention for bits is like MSB to the left and LSB to the right.
LSB to the right. Yeah. I'm actually backfilling things with one.
Yeah. I'm actually new to Verilog, that's why.
Yeah, not an issue. See, the basic thing is, the transition is happening, you're shifting right, and if you reset it, let's say, what is the default thing that happens? Fill it, asynchronously fill the whole thing with ones. Okay, that's what you're supposed to do. If not, if you let the machine go by itself, after shifting the packet, the register should anyway have all ones. So that's what we're doing here. Okay.
Start is a register there.
Yeah, that's a register. I mean, that's a 1-bit value. It'll just signal that I'm starting the transmission. First bit is being sent. That's all it does. We'll see the waveforms also, you can see.
Okay, is that something we can control externally?
Start is something controlled by the controller. See, that's my point. Inputs are only these. These are the things which you remember I told you there's a host and there's a modem and that way. Host controls these things. Okay, it doesn't control the data bus. Okay, these signals are what are controlled by the exclude clock from this. Clock is clocking. These four: byte ready, LED data reg, clock, and reset. These are the only things which host can do. What can host do? Tell that byte is ready. What can it do? It can tell put it to data reg, or start transmission, or reset the whole thing. I don't want transmission. That's all the host can do. What can the controller do? Depending on these inputs, the controller will see, controller is basically the state machine. It will see what state, the machine is in, what are the things happening. Based on that, it'll either tell to start, it'll either tell to shift, or it'll tell to, clear the bit count, or it'll monitor things. So that's how it is. Controller is outputs the signal of start, shift, clear. I had shown in the PPT, right, where I can go back again. These are input signals. Output signals are these. Start, shift, oops. Yeah. I think it's clear. Yes.
Yeah.
Okay.
T byte tells the controller to start transmitting. Is it?
T bytes initiates transmission of a data byte. Yeah.
Okay.
Don't get confused between T byte and start. Okay. Start is just a 1-bit telling that you can just start signals the start of transmission. It'll just tell. Probably it is a signal to receiver. We haven't seen the receiver yet. Maybe when start bit is high, the receiver gets to know that, okay, things are coming my way. And that's when I should start receiving. So start is just a signal just to tell that, okay, it is happening. T byte is something which host controller does it, to start. It wants things to start shifting. So that's the difference. I hope all of you have, pasted it on your EDA playground. Let's just go through the test bench ones. As we have been doing from yesterday, that's the basic thing. All inputs are registers. Output is the wire, like just how it is here. Just paste it here. I've named it as TB underscore UART underscore TX just to know that it's test bench. Okay, test bench is not a module. Nothing gets synthesized. All it does is just provide stimulus to this. How does it provide? You
Your
have to first
PPT
instant.
screen is shared.
Oh yeah, sorry.
Yeah.
God, yeah. Thanks. Okay.
Yeah.
Okay. So all registers are inputs again. All wire. I mean, wire thing is output from here, and instantiate. Call it transmitter. Call it UUT. Call it Skanda. Call it Hippo. Up to you. Okay. And then you have to wire it up. So dot data bus of data bus. Like this is from test bench. This is from the module test bench module. You can either name different things or name it. Just to improve readability, we do this. And then if you know the exact order, I'm just reiterating that again. If you know exact order of what is here, you don't have to do all this dot business, dot or bracket business. Just directly name them. It'll take it. But if there are a lot of things, that's when you use this dot. This kind of syntax. Then you can use any order. I can put data bus here and a serial out here. You can interchange things there. That's up to you. I'm just telling for those who didn't attend yesterday. So yeah, this is our normal thing. I begin with the clock signal being 0, and I after every 5 seconds I tell clock to not be clock. Be the complement of the clock, and that's in an always a block that happens until it encounters a $finish, and then dump file as I already told you what that does. So yeah, coming to this reset, I first reset after let's say some 2 seconds. You can either remove or it's just there. That's it. Timing, you can take care of it by yourself. You can play around with numbers. So when I pull the reset load, that's when reset gets activated. The whole state machine gets deactivated. It just stops, flushes with 1, bit count gets 0, start, shift, everything gets 0. That's what we discussed. Okay. And then what I do, once I do this, I'll fill the data bus with some value. You can give any value. I've given AA. AA is nothing but 10, 10. 10 is nothing but 1010 in binary. So I could give it 8-bit 1010 1010. Okay. So that is what I've done here. At the same time, what I'm doing, I'm also pulling this high. That is, I am telling that data register to go high. That is from the bus, take it to the data register. Then after some time, after the state machine is kind of settled, what I'm doing is byte ready. So I'm asserting byte ready, telling that okay, you can take the byte and it is ready for transmission. Then T byte asserts the transmission. That begins the transmission. And that's all I have to do. Like that's all is in my control. I'm being a host, so I'll just give some 200 seconds in order for things to happen. You can give few more values if you want to, and I give a $finish. So I think that should be enough if I run it. I'm just saving and okay, everything should seem fine. Let me run. Let's see if there are any errors. There aren't. Okay, if you get something like this, press get signals. Okay, you can either take everything up and all, it'll just up and all, transmitter up and all. There'll be some some of the things which are repeated. I'll just remove them. Clock is there once, another clock which is not required. Reset is here, so I don't require this reset. Anything else? What reset is shift? Okay, T byte and T byte. Okay, this T byte is not required. I'll just remove it. Doesn't matter if it is there, but why simply take it? Okay, LED TX, these are 2 times, so I'll remove this also. And TX data reg, TX, anything TX, next state. Is anything repeating? Can you see? Clear. How many
Data
times is
bus.
clear? Which one?
Data bus.
Data bus. Okay, once here, once there. Oh, okay. Okay. I hope that okay, serial out. There are 2 times. Okay. I hope that's it. We have all of our signals. Now, if you see at the 12th second, can you see when you see the data bus here, right? It has literally nothing, XX unknown value. And at 12th second, it is getting the value of AA. Now, why at 12 seconds? Can you see this? 2 plus 10, that's when reset goes low. And at the same time, what we are doing, giving data bus equal to AA. That's basically what's happening here. So you get the value of AA, and then that's there like on the bus all the time. And when you can just analyze like here, reset is at the same time, I pull the reset high again, so things become deactivated. And that's when I can start things. Now, the most important thing is serial out. Can you see serial out getting the value from here? This is a start bit, till here it was flushed with ones. Half of this 0 is like the start bit. This part is 0. Then what is my data? AA, right? 1010 1010. and I'm shifting right. So 0 is the LSB and the 1 is the MSB. Okay, the last one. So first 0 gets transmitted, that is the second half, then a 1, 0, 1, 0, 1, 0, 1, 0, 1 until here. Okay, until somewhere around here, I guess. Yeah, this, and then flush the whole thing with ones after things are done. So that's the output. You can have the bit count also 0, then 1, 2, 3, 4, 5, 6, 7, and then it goes on. So that is one thing. And then clear signal, clear, when are we doing it? When are we clearing it? Okay, we don't do it. Clear is not something which we control. Sorry. Okay. And then what is something in our control? We can see the value of shift register and data registers also. These are yeah, at the same time, data register gets the value of the bus. When does it get the value of bus? When I exert the byte ready. When am I exerting the asserting the byte ready? After is it 22 seconds? 10% 22. Yeah, at 22 seconds. Let's see what's happening at 22 seconds. 22. Okay. One second. 22 seconds. I'm exerting the byte ready. Oh yeah, I'm exerting the byte ready. And then at the next positive clock edge, see, at the positive clock edge, it won't happen like immediately. It'll wait for the clock edge to be positive, and then it puts the data. So that is one thing which I wanted to tell. Shift reg, yeah, goes high and goes low. That's what we do. That's basically it. So our module is working. We just built our UART transmitter. Okay, then thank you all for attending today's session.